The next example is an application of this, and probably you saw similar example in physics. So you have a 100-pound weight hangs from two wires. As illustrated below, I'm going to draw a little illustration. Find the tension forces T1 and T2 on both wires. So, Warren, this is the opposite of, not the opposite, but the reverse of the problem in the homework, where in the homework you were given the tension, but you need to find the weight, I think. So, to illustrate, let's say this is some sort of, let's say this is a ceiling, and you have a weight that are not really in the center. It's like so. So it's hinged here. The wires are connected, hinged to the ceiling, here and here. This is the weight of 100 pounds. So, and here's the tension force T1 on this wire, T2 on this wire. The angles are 50 degrees and 32 degrees, I think. Doesn't matter. We can say theta 1 and theta 2. Let's put numbers here, 50 and 32 degrees, right? So how are we going to go about it? Well, obviously each force, the tension force, can point only in the direction of the wire. So we're going to break the forces into horizontal and vertical components. So if I'm looking at this, T1 is a vector, right? So let's say this is vector T1. Notice that it's different than T1. This is the magnitude. This is just the magnitude. And T1 and T2 without the vector symbol, okay? And the angle here, if this is 50 degrees, the alternative interior is 50, and this angle will be 130 degrees, right? So if I'm going with the standard angle. The other vector, T2, so this is T1, this is T2, has 32 degrees, again, alternative interior angle. So what are the horizontal components? One thing that we know that there is the sum of the vertical component of T1 and T2 will equal the weight, and the horizontal component of T1 and TU balance each other. That's from physics. If we do free body diagram, that's what we come up with. So we're going to say that vector T1 is made of a horizontal component, which will be T1 cosine of 130 in this case, plus, so that will be in the I direction, and in the J direction, it will be T1 sine of 130 degrees, okay, in the J direction. And T2 equals T2, the tension, and it will be, again, cosine 32 degrees in the actually, I switched it, the I and the J, so I apologize. Let me make a quick correction here. No, actually, I was right. It's cosine. It's cosine of 130 I. And here we have T1 sine of 32J. All right, and what we say that the weight, 100 pound, is balanced out by the J direction. So it's equals to T1 sine 130 plus, actually, let me put another vector mg here, and let me write it in vector notation. Vector mg has only j component, okay? T2, yes. Vector mg is equals 0I minus 100j, okay? Because it's negative. And now we're going to say that the sum of the forces in the vertical direction is 0. So we're going to say that sum of vertical component equals 0. And we're going to say that T1 is sine 130 J plus T2 sine 32J equal 100 or minus 100 pound J equals 0. And from here, the only, that would be one equation. And the other, the sum of horizontal component is 0. So the horizontal component only, we have only 2 because the weight has 0 horizontal component. So we're going to say that cosine 130J plus cosine 32J T1 and T2 equals 0. Okay? Notice that cosine of 130 degrees is negative and cosine of 32 degrees is positive. So you have two equations. You have equation 1 and equation 2, and between the two equations you can solve a system. Okay? Those are I. Thank you. There was a correction here, and the horizontal component are I. So cosine T1 cosine 130 degrees I plus T2 cosine 32 degrees J equals 0. And basically what you have a system that looks like this: A T1 plus B T2 minus 100 equals 0, and C T1 plus D T2 equals 0, and you solve for T1 and T2.